Everyone assumes iron armor replaced bronze armor the same way iron swords replaced bronze swords. Better metal, better protection. End of story. Except that's not what happened. Bronze armor remained superior to iron armor for 400 years after iron swords became standard. Warriors fought with iron weapons while still wearing bronze protection. This isn't about metallurgy. This is about why technological transitions don't happen the way we think they do. The timeline problem. Iron swords appeared around 1200 BCE and became common by 1000 BCE across the Mediterranean and Near East. You'd expect iron armor to follow immediately. It didn't. Effective iron armor doesn't show up in the archaeological record until roughly 800 to 700 BCE. That's a 300 to 400 year gap, where soldiers carried iron weapons but wore bronze armor. This creates a paradox. If iron was better, why the delay? If bronze was superior, why did weapons switch first? The answer reveals something crucial about how materials actually perform under battlefield conditions. What bronze armor actually was. Bronze armor from 1200 to 800 BCE represented the peak of Bronze Age metalworking. Smiths had perfected bronze techniques over 1,000 years. They knew exactly how to create plates with uniform thickness, how to shape curves that deflected blows, how to attach pieces for maximum coverage with minimum weight. Bronze armor wasn't cast into final form. That's a critical misunderstanding. Cast bronze is brittle and weak. High-quality bronze armor started as cast ingots, roughly 10 to 12% tin mixed with copper. Smiths then hammered these ingots into thin sheets, working the metal cold. This process, called work hardening or cold hammering, fundamentally changed the bronze's structure. The repeated hammering aligned the metal's grain structure, making the surface as hard as early wrought iron, sometimes harder. A bronze cuirass from this period was hammered to around 1 to 1.5 millimeters thick while maintaining protective capability. The work-hardened surface resisted penetration effectively. A full bronze cuirass weighed 12 to 15 pounds, heavy but manageable for extended combat. Bronze is a homogeneous alloy. The copper and tin mix uniformly at the atomic level, creating consistent material properties throughout. When a weapon struck bronze armor, the metal's slight flexibility allowed controlled deformation that spread force across a larger area. This prevented the concentrated pressure that causes armor failure. A bronze breastplate could take repeated blows from bronze or early iron weapons without catastrophic failure. The manufacturing process mattered too. Smiths could shape bronze through hammering into anatomically fitted armor with curves and ridges that deflected weapons naturally. The result was armor that was both protective and relatively lightweight. Why early iron armor failed? Early iron armor was objectively worse than bronze in almost every measurable way. The bloomery process that produced early iron created a fibrous, inconsistent mass full of slag inclusions. These slag pockets created weak points throughout the metal. Under stress, early iron didn't deform uniformly like bronze. It delaminated, splitting along the fibrous grain structure where slag created planes of weakness. When hammered into thin plates for armor, this iron lacked the strength to resist weapon impacts effectively. Iron armor from 1000 to 800 BCE shows a consistent pattern of failure in archaeological finds. Plates are thicker than bronze equivalents, typically 2 to 3 millimeters, because thinner iron simply didn't provide adequate protection. Here's the weight problem. Iron is slightly less dense than bronze, about 7.9 grams per cubic centimeter versus bronze's 8.8. You'd expect iron armor to be lighter, but the extra thickness required for safety more than canceled out the density advantage. A full iron cuirass from this period weighed 20 to 25 pounds, 60 to 70% heavier than bronze armor, providing equivalent coverage. The weight penalty alone made early iron armor tactically inferior. Soldiers fatigued faster, moved slower, and had reduced endurance in extended battles. In formation fighting where mobility and stamina determined survival, this disadvantage was severe. Impact resistance was worse. Early iron's fibrous structure and slag inclusions meant weapons could penetrate or deform iron plates more easily than work-hardened bronze. When an iron sword struck an iron breastplate, the blade could punch through weak spots or create dents that compromised the armor's integrity. Bronze armor resisted this penetration better because its homogeneous structure and work-hardened surface prevented catastrophic failure. Corrosion was another critical problem. Bronze develops a protective patina that slows further corrosion. Iron rusts, and rust weakens the metal continuously. An iron cuirass exposed to battlefield conditions. Sweat, blood, rain deteriorated rapidly. Maintaining iron armor required constant care. Oil application. Storage in dry conditions. Bronze armor could be neglected for months and remain functional. The production problem. Making effective iron armor required solving problems that took centuries to figure out. Bronze armor could be hammered from cast ingots using techniques smiths had perfected. Iron armor required entirely different processes because iron couldn't be cast at temperatures achievable in ancient forges. Every piece of iron armor had to be forged, meaning smiths had to heat iron repeatedly and hammer it into shape. This was labor-intensive and time-consuming. Creating a single iron breastplate took 3 to 4 times longer than hammering a bronze equivalent from cast ingots. For armies that needed hundreds of armor sets, this production bottleneck was decisive. Quality control was another barrier. Bronze from properly mixed ingots produced relatively consistent results. Hammer the bronze, work-harden the surface, and you got predictable armor quality. Iron forging produced wildly inconsistent results. The same smith using the same techniques could produce strong armor one week and weak armor the next because bloom iron quality varied with each smelting. This inconsistency meant armies couldn't trust iron armor uniformly. A soldier-issued iron armor might have adequate protection, or might have armor that would fail in the first serious engagement. Bronze armor's consistency meant commanders knew what level of protection their troops actually had. When economics finally forced the switch, iron armor didn't become standard because smiths figured out how to make it better than bronze. It became standard because bronze became impossible to produce at scale. The Bronze Age collapse around 1200 BCE destroyed tin trade networks across the Mediterranean. Afghanistan, Cornwall, the sources that supplied tin for 1,000 years became inaccessible. By 900 to 800 BCE, bronze production capacity had collapsed. Existing bronze armor became incredibly valuable, carefully maintained, and passed down through generations. Archaeological evidence shows bronze armor from this period, with extensive repair work, patches, reinforcements, anything to keep it functional. Armies needed armor. They couldn't get bronze. They had to use iron, so smiths worked on making iron armor less terrible. This took generations of experimentation. They learned that repeated heating and folding reduced slag content. They discovered that certain iron blooms produced stronger armor than others. They developed techniques for surface hardening, creating harder outer layers on iron plates. By 700 BCE, iron armor had improved enough to be tactically viable. It still wasn't as good as bronze armor of equivalent weight, but it was available. Smiths could produce iron armor using local ore without depending on international tin trade. For military logistics, availability trumped quality. The transition shows in archaeological evidence. Bronze armor from 800 to 600 BCE shows extensive repair work. Iron armor from the same period shows rapid increases in quantity but relatively poor quality compared to earlier bronze pieces. Armies were making the best of a bad situation. The carburization revolution. Iron armor didn't surpass bronze armor until smiths developed effective carburization and early steel production techniques around 600 to 500 BCE. Carburization, heating iron in contact with charcoal to infuse carbon into the surface, created harder outer layers that resisted penetration better than work-hardened bronze. Steel armor, iron with controlled carbon content throughout, finally exceeded bronze's protective capability while matching its weight efficiency. A steel cuirass could be made thinner than bronze while providing better protection. This was the actual technological breakthrough, not the simple shift from bronze to iron. But this development came 400 to 500 years after iron weapons became standard. The material transition happened in stages, driven by availability first and quality improvements much later. What this actually means. Bronze armor remained objectively superior to iron armor for centuries after iron swords replaced bronze swords. Warriors fought with mismatched technology because swords and armor faced different constraints. Swords could be made from inferior iron and remain functional. Wrought iron was soft and required frequent sharpening, but it could still cut and thrust. Armor made from the same iron was dangerously inadequate. Protection requirements were stricter than weapon requirements. This created a technological lag. where weapons transitioned first, and armor followed only when economic necessity forced adoption of inferior materials. The pattern repeats throughout military history. New materials or technologies often start worse than what they replace. They win because of availability, cost, or production scalability, not because they're immediately better. Then centuries of refinement make them actually superior. By that point, everyone's forgotten the new technology started as a downgrade.
Bronze armor outperformed early iron armor because metalworking maturity matters more than material choice. The real story isn't about iron beating bronze. It's about how collapse and scarcity force technological transitions before the replacement technology is actually ready. Understanding that difference changes how we see every major material shift in history.